The topics to be covered are kinetic energy, potential energy, work energy theorem, conservative and non-conservative forces. Why do we say that when we raise some object, it acquires potential energy? When we raise something, then it is capable of doing work if we allow it to fall. When we hold something up at a height, then the potential energy remains in it. When we take a hammer and a nail and want to nail it in this wooden piece, the common experience is that you would put the nail there with its sharp pointed end touching the wood, the head of the nail above it, and you take your hammer and you raise it to a particular height. What is the reason to raise it to a particular height? After all, it is this particular activity which is required. You raise it to give it a certain potential energy, and when you allow it to fall on this head, then it converts that potential energy into the energy required to push the nail inside the wooden piece. What is meant by potential energy is with respect to a particular level. Is this leveling required? Let us take it by imagining this to be a staircase. When you are on the ground level, the potential energy is 0. When you are higher, the potential energy is increasing. What about a person who is standing somewhere here and another person who is standing on the top? So, with respect to this person who is already at a particular height as compared to the ground level, the potential energy is different. This experience you might have had if you have played with a ball on stairs. The ball would roll down and it would be acquiring different speeds. The reason is that once it comes down from top, comes to a particular level, the potential energy changes, and then with respect to the other, the potential energy is quite different. Is work done equal to 0 if displacement is 0? Not necessarily, especially if there is friction involved. If something goes on any particular surface in a loop and returns back to its original position, though you calculate work in terms of force multiplied by the displacement, this displacement being 0, you still call it 0 work done, because some work would be done against the dissipative forces of friction. How much work is done by gravity on an object moving in a horizontal circle? Or how much work is done by the centripetal force on a body which is revolving around a circle and the circle is in the horizontal plane? To help you imagine, I have this loop and imagine an object going round like this. Now, the two forces that we have talked about, one is gravity, which would be acting on the object as it goes right around. But notice the displacement is along the curve, but the force is acting perpendicular to it. So, gravity does no work if it is rotating in a horizontal circle. Similarly, imagine the centripetal force required to keep the body in the circular track. Now, if it is moving here, this centripetal force is acting towards the center. In a horizontal circle, this can be imagined like this at different locations. So, the object is moving in this direction and the force is perpendicular to it. Because of this reason, again centripetal force does no work. You must have seen at construction site workers taking bags of cement, bricks to a particular level. Now, if another crane is doing the same work, lifting the bricks or the cement to the same height in much less time, do you think they are doing the same work? Yes, because the height gained by the cement bag or the bricks to take it to a particular level is the same. It is the time which is different or the effort which is different, but the potential energy gained by the cement bag or the bricks is the same in both the cases, whether it is taken up by the construction worker or by a crane. You've all seen springs. Now, the spring may be compressed or elongated. Now, when do we say that potential energy is stored in it? Notice, if I were to stretch this spring, I will change its length, I will increase its length. Am I storing potential energy? Or when I compress it, is the potential energy being stored? In both the cases, because the deformation is taking place, energy is stored in both the cases. That means when you compress it or when you elongate it. What is meant by zero potential energy of a spring? The zero potential energy is associated with its unextended length. That means when it is neither compressed nor elongated. This is its zero potential energy. And as we have said, we have to have a reference for zero potential energy. For example, if you remember the experiment we did with the load extension graph, and we had a spring and we were loading it, and you could see that this spring would go up and down. So, in connection with that, remember that the new displaced position of the spring on account of a certain extension that you created in it, now whatever deformation you give to it is going to be responsible for telling you the zero potential for that spring. So, you can change the zero potential energy of the spring by loading it and thereafter causing compression and elongation in it. K is supposed to represent the spring factor. Now, the spring factor K, you say, is very large for a particular spring and less for the other. What is meant by that? It means that the stiffer spring for which the force per unit length is larger, that means you need a larger force to extend it by a unit length, then that becomes a stiffer spring. The springs used in the motorcycles are stronger as compared to the springs used in cycles. You might have noticed it under the cycle seat, you have a spring and which compresses and elongates as the person moving on the cycle goes on the road. If the road is smooth and straight, there is no jerk, but supposing there is a little damage in the road, then the cycle goes into that pothole and comes out. In order to keep the balance for the cyclist, in order to keep him safe, these springs are provided under the seat. The stiffness of the spring is determined by who is going to sit on it. If it is meant for the cycle is meant for a small child, then so much stiffness is not required. But for an adult cycle, this has to be taken into account as to how much weight would be sitting on account of the man sitting on the seat. If spring A has a larger K value as compared to spring B, in which case would you need to do more work to compress it by the same amount? That's easy to figure out because work done is equal to the energy stored in it, and we have calculated or learned to calculate that the energy stored in the spring is equal to half kx square. So, if you put the value of k which is larger, then obviously more work will have to be done. If the k value is smaller, lesser work will have to be done. So, you have to understand the k value, the elongation, the x, and therefore connect the potential energy and how much work it can do. You might have seen that this work done activity is taken into account wherever springs are used in daily life, whether it is at the bow and arrow shooting range in the case of say a game, then you have to see what should be the value for this k, how much of potential energy is going to be stored in it, how much of work will be done on the arrow to take it across to the target, etc. So this is very important. Now let's think about this one. A truck and a car are moving with same kinetic energy. They are brought to rest by applying the same braking force. Which of them will come to rest in a shorter distance? Using work energy theorem, loss in kinetic energy is equal to work done against retarding force. Now the retarding force into the distance travelled would be this value of loss in kinetic energy. So the distance travelled is equal to loss in kinetic energy divided by the retarding force. So both will stop after travelling the same distance. Now notice over here, the truck is very much larger and the car is much smaller. But you applied the same braking force on them and they stopped after the same value. Why? Because their kinetic energies were the same. Obviously speaking, if a smaller object has the same kinetic energy as the larger one, you should be able to figure out that the smaller one must be moving with a higher speed. Now let's look at this one. A truck and a car are moving with the same kinetic energy on a straight road. The engines are turned off simultaneously. Would the stopping distance of the truck and the car be the same? This problem is different from the earlier one. What's the difference? Though they were travelling with the same kinetic energy, the engines were just turned off. It was not an additional force or the braking force applied here. So how will we figure out what will happen in this case? Now loss in kinetic energy is equal to work done by force of friction. Force of friction multiplied by the distance travelled before stopping. Or we can say loss in kinetic energy is equal to F into S. Now the force of friction is going to be on account of the motion on the road. So coefficient of kinetic friction multiplied by R, R being the normal force acting on the car or the truck. So what will it work out? Loss in kinetic energy is equal to mu R into S or mu mg into S. So S is going to be inversely proportional to the mass. Therefore, the car will stop after travelling a larger distance. So the car will stop after travelling a larger distance. If I cut the spring into half, will that change the value for spring constant? What does it mean? It means I cut the spring into half, so I have two pieces of spring. Now the force required to elongate it by the same amount or compress it by the same amount or length, will that remain the same or will it change? Well, it will change. Why is the SI unit for spring constant Newton per meter? As we've described the force constant or the spring constant of a system which has the restoring force building up in it, defined by the force per unit compression or elongation. Therefore, Newton per meter becomes its SI unit. What would be its dimensions? They would be m L0 t raised to minus 2. How did we get that? The dimensions of force, which are m L t minus 2, and dimensions for compression or elongation m0 L t0. So if you were to calculate that, you would get m L0 t minus 2. There is a lot of potential energy, kinetic energy conversion taking place at the sports fields. Have you ever wondered why a bowler has to have a run up before he delivers the ball? The reason is that as the bowler runs up, he gives that kinetic energy, same as what his speed is, the speed of the ball is the same. If it wasn't so, the ball would be left behind. So both of them are travelling with the same speed. So the speed of this ball is also the speed of the person. So, the kinetic energy that the ball has is going to be in terms of the mass of the ball and the velocity of the ball, given by half mv square. So, this additional kinetic energy allows the bowler to deliver it at a particular speed which he desires to do. Javelin throws, discus throws, all of them have a lot of activity by the person before they actually go ahead with the event. What will be the ratio of kinetic energy when the car is at 25 kilometers per hour to when it is moving at 100 kilometers per hour? If you work this out, you will find that the car at 100 kilometers per hour has 16 times more energy as compared to when it is moving at 25 kilometers an hour. It is for these reasons that the speed limits are set up in the city. You cannot have so much kinetic energy, and if you were to, should anybody have an accident, it would be very, very lethal. Now, in a car, when you go to buy a car, they tell you the power of the engine. What is the meaning of that? They want to say how fast would you be able to change your speed from a nominal value to a higher value. And let us say that if you are talking about acceleration for a car moving at 25 kilometers per hour to reach up to 100 kilometers per hour in say about 12 seconds. What would be the power of that engine? So, how will you calculate that? You will find out the change in kinetic energy. You will therefore find out how much of work is to be done, and then you will find out how much of power is there. So, work done divided by the time in which you want the engine to perform the activity is going to be giving you the power of the engine. So, when they say the power is so many horsepower, that means the watt or kilowatt that you calculate is converted to a commercial unit as horsepower. Are there other kinds of potential energies? Yes, there are. The concept of potential energy is much more general. It refers to the energy anything or something that has as a consequence of its position, regardless of the nature of the force acting on it. The earth itself has potential energy with respect to the sun for its orbital motion around the sun. Electrical and magnetic forces also create potential energies. The electrical energy is stored in objects that have charges. The magnetic energy is stored wherever there are magnetic forces acting. You will learn about these as you go along the way. So far we have only talked about potential energy, which is related to mechanical work. So, mechanical potential energy. This mechanical potential energy is responsible for doing a large number of jobs for us. So, it is important that we understand it clearly.